Okay, so when I was a boy, I had a couple of computers. These were my first two computers right here. TRS-80 color computer. When I got my first programming job a few years later, it was one of these, a Commodore 64. And at the time, so at the time, this is what programs look like. This is what BASIC looks like. You've got like this asks what your name is, you type it, and then it prints your name over and over again all over the screen. And sort of the essence of what programming looked like back then looked like this. And the line 20 there, the semicolon makes it stay on the same line, and then the 20 go to 10. This was like the first thing that I wrote when I was a boy. And um, this talk is what I wish somebody had given to me at the time. So in particular, sort of the mindset that I had at the time was, well, actually, let me show you another program here. So I would write little programs like that when I was first getting started. But occasionally I'd come across little programs like this, where you'd have these mysterious data statements, right? And I'd type this in carefully off of a magazine or something, and I'd run it, and it would do amazing things with graphics and all kinds of stuff. And I would tell myself, okay, there are people out there who are much, much smarter than me, demigods, and I'm just not smart enough to be able to understand this stuff. They're on another level, and I'll never be able to get there. And that sort of mindset was poison. And this is the spoiler here. This is machine language, is what's going on here. Let me just tell you what this program does. Clear clears the screen. This prints a character to the screen, a graphics character, something, I don't know. And then this for d equals 0 to 73, I presume that there's 73 numbers sitting down here. The read statement in BASIC reads a data value, and it keeps a pointer. And every time you call read, it gives you the next data value. So this is basically some embedded data. And then they're doing a poke, 828. The poke command takes a value, which we've got in Q, and it sticks it into a memory address defined by this 828 plus D. All right, and D is going from 0 to 73. So this is just taking these values and sticking them into memory. And then sys 828 starts executing at memory location 828. And anyway, this is machine language. And like, I just found this to be so mysterious, so inscrutable. And in this talk that I'm giving you here, I'm going to dispel some of the things that make that mysterious and help you understand it. And I wish somebody had explained this to me when I was a boy. So by the end of this talk, you'll be able to answer all of these kinds of questions. What's machine language? What's assembly language? What's the difference between machine language and assembly language? What's an assembler? What's a disassembler? Do you guys know the answer to any of these questions yet?
I not confidently.
Yeah, I was
Okay.
gonna say
You,
not
you,
really.
you'll be able to
Yeah.
confidently answer all of these things by the end. If
I
you
could
wanted
I
to
could have a
write,
wild conjecture.
if you wanted to write an assembler, how would you do it? You'll know that by the end of this. What if you wanted to write a CPU emulator? Could you do that? What does this stuff mean? All right, the spoiler is that's a program. What does it do, and how would you even be able to begin to figure out what it does? You'll be able to do that by the end of this. And then when you see stuff like this, which we're going to be looking at here shortly, what does this even mean, and how do you make heads or tails out of it? How do you write code in assembly language or machine language? And if you had a game sitting in your memory on your computer, how would you hack it or modify it? Um, there's a machine like this sitting in the Microsoft museum. What do you suppose these buttons and lights mean and do? By the end of this, you'll have an idea. Okay, so let's jump into it. This is a programming thing, and I'm starting with chips. Seems weird for us modern programmers to think about chips, but anything you do with machine language, you always have to start with the chip because what you're doing is you're programming a very specific chip. This particular one is a 6502, which is a microprocessor. This is the same microprocessor that's in the Atari video game system. It's also the processor that was used in the Nintendo, the original Nintendo, all kinds of other things. The Atari 400, the Atari 800, lots of different video game consoles from the 80s all use this chip. The reason you have to start with the chip is because machine language is programming that very specific chip. So let's dive into what this chip does real quick. And I'm picking one because I have to pick a specific chip in order to talk about assembly language. Each chip has its own different, each kind of chip has its own different language, but there's a lot of similarities and it'll make sense to you later. So let's dive into what's in this chip if we're going to program it. A chip, a microprocessor has several registers. The 6502 in particular, it's an 8-bit processor. And the reason what that means is all of these registers are all 8-bit registers. So it's got an accumulator called A, and there's 8 bits in it. So that means it can store values from 0 to 255. It also has a couple of other registers called X and Y. Now, if you want to do anything with this chip, or when you program it, let's say that you want to set a value in memory. The way you do that is load a value into the accumulator, A, and then store it back out to memory somewhere. And I'll show you some examples of that. In fact, let's dive into a very particular computer that uses this. We're going to use this one right here. This is called a Chem 1. And here's the user manual for the Chem 1 from August 1976. It actually looked like this. And we'll start I'm going to hit the address button here. And what I'm doing here,
Richard,
yeah?
when you say it looked like this, what was this? Was this a toy?
No, this
Was
was
this
a hobbyist computer. You could buy
okay?
these. You can still buy them on eBay now, actually. But it's a computer and it's got, these are the RAM chips. One of these is the microprocessor. I'm not sure which one. It had some input and output, had this little 7-segment display. You could hook a teletype up to it. You could hook a tape recorder up to it to load and save programs and so on. All right, so let's talk about what these buttons do, all right? When I hit AD, that puts me in address mode. And if I hit plus, what we're seeing here, the first 4 digits, that's a memory address. And then the last 2 digits is showing me the value that's in that memory address. Okay, and the Chem 1 has a particular memory map in values, in memory addresses 0 to FF, that's called 0-page memory. 100 to 1FF is the stack, and 200 plus is the RAM. Notice those numbers have Fs in them. That's hexadecimal. All that is as I hit the plus button here, notice the numbers go up. Like we're at 60, now we're at 6, 1, 2, 3, 4, 5, 6, 7, 8, 9. Instead of having per character, there's 16 values per character, right? So after 9 comes A, B, C, D, E, F. Then we start over and roll back around. That's called hexadecimal. All right, so I'm basically going through, and so as I go up, I'm going through that 0-page memory right here. And then I'm not going to hit this enough times, but after that, so basically these are all RAM values. So I'm going to go and put a value at 0, 8, 5. Oops, hold on, 0, 8, 5. There we go. And now I'm going to stick a value into RAM here. The current value is 0. I'm going to hit DA for data. I'm going to put 33 there. And then I'm going to hit plus. So now I'm looking at 086. So I can actually go back to 085 again. 0, 0, 8, 5. And there's my 33 that I stored. All right. So if I wanted to put values into memory, I can do that. I'll put 33 there, and then I'll put like 34 here, going back to data mode. 34, 35, 36. And then if I went back to the 085 memory address. So all I'm doing is poking values into memory. All right. So now if I hit plus, you'll see my numbers going back up again. Make sense so far?
Yeah.
So you don't have to put numbers in. You could put the letters in as well. You could set it
Yeah.
to A or B or anything
Yeah.
hexadecimal, right?
Yep. So like
Okay.
if I wanted to put beef into memory here, I could put BE. Oops, hold on, back to address mode. 0080. There we go. Data mode. I'll put BE here and then EF here.
Got it.
0080. And there's my BE. There's my EF. Okay.
And one more question. You said that is this the RAM that we're updating?
Yeah, we're updating RAM.
Got it. Okay.
Okay. So now let's write a program. All right. And I've shown that we can mess with memory and go inspect memory.
Right.
So we're going to write our first program here. Now, in order to put anything into and out of RAM, we have to put it into a register first. So I'm going to show you the instruction set for this thing. So this is all very complicated, but what we're going to do is skip down to the load A. So these are all the instructions that the processor can do. Okay. In fact, that's the full list. All of these little 3-letter acronyms, those represent different instructions. One of them, and probably the one that is used more than anything else, is load A, load accumulator. Actually, I'm going to zoom in on this just a bit. All right, so we're going to look at load A, load accumulator, right here. All right, load A. This loads the accumulator with something from memory. Now there
Your
are many.
screen's kind of cut off for me, by the way, Richard.
Which side? Left?
I can't see like the left side fully.
How about now?
Nice.
Oh, I see.
Yeah.
I see what you're talking
Alright.
about. Can you see it now?
Yeah, that I think that's it. Might be
Can
a
you-
little bit more to the left.
More to
But
the
I
left or right?
I mean, I see LDA and the end of the browser page.
Is it just me? Oh.
All right. So can you see it, Bo?
Yeah, that looks better. Thanks.
All right, cool. All right, so load A. There's several different flavors of load A. The one that we want is we just want to take the value, let's say 44, and put it into the A accumulator. So to do that, I use this style, load A and a pound sign. All right. The opcode for that is A9, and it takes 2 bytes. So let me just show you that working. So I'm going to go back here. That's A9. Remember that number. And I'm going to put my program at 0200. And the opcode for that is was A9. All right, so I'm going to put an A9 in memory at this location. So data mode A9. All right, and then let's pick a number like 42 and put it here. 42. All right. Now let's store the number 42 somewhere in memory. Let's put it at 400 in memory. All right. So I'm going to go look at the instruction set, and there is a store A instruction. Oof. Let me get it up here. Store A. Store A. Where are we? Here we go. Store A. There's a store A instruction, and its opcode. All right, there's several different flavors here. If I'm going to put it somewhere on the 0 page, which is the first 200 bytes, 255 bytes, I can use this one. But I want to store it at 0400, so I need to use this style, right? And so notice that takes 3 bytes. It starts with 8D. I'm going to put an 8D here. Data mode 8D. And then the next 2 bytes that come after that are the address where I want to store it. Now this particular processor uses stores things backwards. So the next 2 bytes are the address where I'm going to store it. So I'm going to store it at I want to put it at 400 hex. So I'm going to do a 00 here. That represents the lower 2 bytes, or the lower 2 characters. And then the higher 2 bytes are 04.
Oh,
all right.
okay. Yeah.
So it stores it backwards of what you might
Right.
expect. So now I'm going to go back to 0200 hex where my program is. All right. A9, that's the load A. 42 is the value we're going to load into A. 8D, that's the store A instruction right here.
Yeah.
and then the next 2 bytes are where to store it. So that's 0004, which means 0400 hex. All right. And then the next instruction that I'm going to put in here is 00, which is break, which tells the machine stop what you're doing and return back to the monitor. Hold on, I'll just show you how I know that that's break. Where is it? BRK. Break. Opcode 00. All right. So I've just put in a program that consists entirely of numbers. And before we execute the program, I'm going to go over to 0400 memory where I'm storing this, and you can see that it's currently 0. All right.
Mm-hmm.
Now I'm going to execute my program, and the way you do that is you put in the address of your program, go to address mode 0200, and you hit the go button, and it takes whatever's in the address window right here and starts executing a program there. So I hit go, boom, it just executed my program. And now if I go to 0400 memory, we should see a 42 there.
So
okay, go ahead.
I saw that when you hit go, it took you to 7. Is that after the break? Is that the
I think so. Yeah,
okay.
I think that's showing me the address of where it was at. So if you look at the, hold on, I have it here. The registers on the 6502, it's got the A register, X, Y, S is the stack pointer. And then the 116-bit address or register that it has is the program counter. And so when I hit 0200 and then hit go, it loaded 0200 into the program counter and then resumed execution. And then at the end of executing, it's showing me what the value of the program counter was when it broke out.
Got it. Okay. Yeah. So it would have been right after the last command, essentially.
Yeah.
Yeah.
So we just executed a program, like the simplest possible program that actually does something. And now I can show you something more complicated, but I just want to make sure this is making sense to you so far.
Yeah, it makes sense. It's funny. It's kind of weird and hard to think about how like the code and the data are like so intermingled. You know what I mean? Like
They are.
Thing.
And in fact, one trick that you use in some computers is called self-modifying code, where the program stores things in memory that it's getting ready to execute, which is also the basics of that's actually how you make an assembler, by the way. An assembler, so this is actually, we'll get into assemblers here in a minute, but let's make a slightly more advanced program, okay?
Sure.
Mm-hmm.
Over here, I have in this window here, there's a thing that's got like useful ROM routines. These are things that are sitting in the ROM of this machine. So all a ROM is, by the way, is it's a memory device similar to a RAM, except you can't write to a ROM. It's already got its values burned in. Burned into the ROM of this machine is a number of subroutines that are useful. For example, there's one here that outputs 6 hex character digits on the display. That's this display here.
Oh, okay.
So let's write a program that writes beef on this display. And we have 6 characters, so instead of doing beef with 4 letters, we'll throw an extra couple of E's into the middle of it. All right? Okay. So in order to do that, we know we've got this ROM routine here called scan_ds, which outputs characters on the display. The way that it knows what to output to the display is it's going to read these 3 memory addresses.
Okay, yeah.
And so this is a very common way of doing things in assembly language. You make a routine that does something, and the inputs to the routine come from known memory addresses. Okay.
Just like, yeah, like kind of like arbitrary well-known memory.
Arbitrary well-known memory addresses.
Yeah.
Exactly. So I've got this program here, and I'm going to show it to you that does this. So let me put the program in here. Okay, let me explain to you what I've just done. First, ignore the stuff on the left for a minute. Our program goes like this: load A, $BE. All right. Can you guys tell me what this does?
It loads BE into the accumulator.
Yep. And there's some special ceremonial symbols here. The $sign means that this is a hexadecimal value. So I could, for example, instead say load A 19, and that would be decimal 19. Oops. All right. The pound sign, though, means this is literally the value that we're going to use. All right. If I got rid of the pound sign, what that would do is that would look at memory address 19 and load A with the value that's there. Okay.
Okay.
And so that right there is what they mean by the difference between, yeah, like you see these, all of these things say immediate, zero page, and so on. The immediate always has the pound sign there. That means literally use this value. If you don't put the pound sign there, then it takes this value and it goes and fetches it out of memory.
Okay.
Reminds
That
me of
makes
like
sense.
dereferencing a pointer or something.
It
like
is
that.
exactly like dereferencing a pointer. In fact, some of these others are even more like dereferencing a pointer. There's a couple of other modes as well. If you put the comma X there, what that does is it grabs this value out of memory and then it adds X to it. So X is like an index pointer that advances you through an array.
Oh, yeah. So that's
Okay.
very C-ish.
That's very C-ish. And then this one is also very C-ish. What this one does with the parentheses is it takes that memory location, adds X to it, and then that is a pointer value in memory, and it goes and gets that value and uses the address that is there.
Can we go back to the program really quick?
Yep. This one?
Yeah. So the first thing that we do is we load BE, and I get that we need the pound sign to make it so that we're not going to memory address BE.
Mhm.
We're actually
Yep.
talking about the hexadecimal BE. But
Mhm.
what's the $sign for?
$sign means it's hex.
Got it. But like, does that mean that in every single memory, there's like a secret, like it's keeping track of its type, or is this just to say, like, to the command, this is how we're entering it in?
It's telling it. So for let's say that I wanted to load the value 32 into memory. Okay.
Yeah.
Like suppose I wanted to do load A and I want the value 32, and I mean decimal 32. All right. And I did that. Notice we've got this A9BE here. Okay. The reason that the A9BE there is the 89 is the load A immediate mode value. So let's go look at load A real quick. All right. A9 is immediate mode load A. All right. And then the next byte is the literal value there. Okay. So if I had load A 32, I want to put the number 32 into memory. What it would show over here for the actual values that translates to is it would be A920 because 20 in hex is 32. 16 times 2 is 32.
Right.
The purpose of the $sign is to tell us that this value is hexadecimal, not decimal.
Got it.
So actually here,
Okay.
let me show it to you in a slightly different way. I'm going to write a program here. Load A 32 and hit assemble. And it made A920.
Okay. So it
And if I did 33 and assemble, now it's 21 because 2 times 16 is 32 plus 1 is 33. And if I put a $sign here, then it does that because the value 33 in hex is 3 times 16 is 48 plus 3 is 51.
it's kind of surprising that decimal is the default. You would think that hex would be the default and decimal would be like
Yeah.
what you would
Yeah.
tag, but
That's just the nature of the assembler. You don't have to write an
Right.
assembler that way, but that's what people have always done.
right.
What even happens with BE if you put it in decimal mode?
You can't put BE in decimal. It's not a value.
Got it. Okay, so
It's
it
not
just
a
like
number.
throws.
Well,
Yeah,
I imagine
that
it
makes
would throw. Let's see. If I say BE here, what does the assembler do?
Yeah.
Nice. Cool. We're
Undefined
25 minutes
symbol
in and we already
BE.
got the assembler to fail.
Now, what you can do though is you can do
Oh,
You can do this sort of thing. You can make constants.
that's nice.
So 12 in hex is the value C. Does this make sense, Jackson?
Yeah, perfect.
Okay. All right. So, right, back to our program. Okay. So load A, BE. We know from looking at our little chart that load A for immediate mode is an A9. All right. And then store A at F9. And where I got this F9 is if you look at our list of useful ROM routines right here, this scan DS, it's looking, at F9, that's just one part of the ROM routine of where it's going to look for stuff.
Oh,
All
these
right.
guys, all the memory addresses have dollars in front of them too.
Yeah.
Got it. Anytime you're dealing with hex,
You
there's a
want to put
dollar sign somewhere.
exactly.
Okay. And at this time we don't have our pound because we're actually dealing with memory.
Exactly.
I
Load
got
this literal value, store this at that spot in memory. Load that literal value, store that in memory. And
Cool.
then JSR scan DS. Now JSR, you haven't seen that before. Let me show you what that is. It stands for jump to subroutine. JSR. Yeah. Jump to subroutine. Its opcode is 20, and it's a total of 3 bytes. So you put a 20 in there and then 2 bytes, and that tells it where to jump to. All right. And so back in the day, if you didn't have an assembler, what you would do is you'd write your program out like this in paper, and then you would painstakingly go to that little your user manual, and you would figure out that's an A9, and then we want BE. And then store A is 85, F9 is the location where we're going to store it, and so on. And you figure out all of these things, and then you go type your, oh, and then JSR we just mentioned was 20. Scan DS, we know from looking at our manual here, is at 1F, 1F. Hold on, I'm trying to find this. Man. Oh, I see the problem. I've got to go down here and scroll this scroll bar to the left. There we go. Yeah, so scan DS, this routine is at 1F, 1F. All right. So that's why in my little program, I wrote, 20 is JSR, 1F, 1F is where we want to go. And then there's this other subroutine called get key. Oh, anyway, that's you get the basic idea.
Wait, I want to make sure I get the basic idea. So scans, I'm looking at the JSR scans. Scans is the name of a subroutine.
Yep.
And so that's like a variable that was kind of set like on
Set
this
above.
device or something.
No, the device already comes with stuff programmed into memory. So it's not a variable that's set, it's a ROM that contains software.
Right, but I guess the like at some point, like scans at some point is set as a variable that references a spot in memory.
Yes. Yes. And so you have
ours-
to type it into your assembly program, basically. Actually, we're not even using an assembler. We just know that scan DS is at 1F, 1F.
Right.
And so when I wrote my program here and I said JSR scan DS, and I'm over here, I'm translating it into machine code. And so I know that 20 is JSR and that scan DS is 1F, 1F.
But so sorry, so scan DS was set by the ROM somehow?
Yeah.
Or okay, interesting, got it. So
The
when
way
we
it was
look up-
set in ROM is somebody wrote all the software that's in ROM, and that's where scan DS ended up landing.
I think maybe what Jackson's getting at is like when you go to like actually enter this into your computer, you're not going to enter in scan DS. Obviously,
No.
You're going to enter in 1F, 1F.
Correct. In fact, let's enter it in right now real quick. So basically what you do is, just like we did earlier, we're going to go to this location in memory, 0820. And then we want A9BE to be sitting here. So I go A9 plus, and then BE goes into the next memory location. And then 85F9. And then we keep doing this, but that's rather tedious. But that's what you do. You very carefully type
Right.
in your program one byte at a time.
Oh, I see. Because we're actually going to just type in 1F1F, and 1F1F is where that program is stored. We don't
Yep.
type in scan anything.
No, we are going to type 2020. So actually, I'm at 824 right now. I'll just finish typing this in. At 824 goes A9EF. So I'm going to put that in real quick. A9, then EF. And then what else? Then what? Let's see. At 826, we want 85FA. 85FA, was it?
Yeah. Yeah.
And then 20, 1F, 1F. 20. And here's where we type in scan DS, 1F, 1F. And then, yeah, at this point, it starts to get a little wonky. I'm actually going to change this program here. I was playing with something. I'm going to make this a little simpler. Insert above. And what I actually want, I'll insert another blank line in here. Insert above. There we go. I'm going to do jump. Basically, I'm doing a go to this line here. So jump -3.
By the way, Richard, you're uh, you should move the OneNote to the left of your screen.
Oh, yeah. Okay. So at this point, it's already clear that typing these things in sucks, right?
Yeah.
All right. That's what assemblers are for. And so what an assembler does, and we already kind of showed that a second ago, is it lets you type a program in and let a computer do the translation for you. All right. So I'm going to show you one here. I've got an assembler here that's online. Now, back in the day, you would do this by hand, but you would like dial into a mainframe and let the mainframe do the assembly for you. And anyway, so let's look at this program that I've got here. I've defined scan DS as 1F, 1F. I've also defined get key as 1F6A. And I defined a couple of things. ORG840 is a directive that tells it I want to start locating in 840 in memory. And then I've got these things, the program here, very similar to what we did here. And then I did jump halt. Let me assemble this and see if it works. Nope, it didn't work. What's wrong? Legal character dot dash dash. Do I have a dash? Oh.
Nope.
Okay. So it just assembled my program, and these are the values that it assembled it as. And so you can see that it did, starting at 840 in memory, here's my program. And then going at 848 in memory, here's the rest of it.
Now, this wouldn't fit on your little computer where you only have 2 hexadecimal characters per space in memory.
Right. What I would probably do, there's a couple of ways I could do it with my little computer. One way is I could put this onto a paper tape and feed it in. Or I could print this out and just use this as a reference as I type it in. But
Yeah.
this little computer actually has an assembler built into it, which I'm about to use here. And I'm going to click assemble. And it's asking me where to assemble it at. And I'm going to say, oh, 840. Okay. And now it just assembled that into memory. So now if I go look at 840 in memory. It should be sitting there. Let's see if it is. Address 0840. That didn't do what I expected. Oh, syntax error. 1F, 1F.
Is there like white space before your?
Okay, actually, I'm going to do this a different way. I'm going to use this other assembler from over here. I'm going to take this stuff and I'm going to put it in here and hit upload.
Oh,
can I do that?
Can you disassemble and then reassemble it?
I don't know. Okay. Let me switch over. Go ahead.
Is there a way, I assume, to just like clear all the memory? Easy way to do that. Okay.
I don't know. Okay. I'm using a different emulator here.
Sure.
Load memory. Okay. So now if I go over to this guy and I say show memory starting at 840, it's got it loaded.
Ah, cool.
Oh, but this isn't going to help me because I wanted it over on the other emulator to show beef on the display. Okay, let's go back to this one.
It's so fun. I recognize that format. Like hex dumps always have that.
Yeah.
But I've never like been able to make sense of it.
So I'm going to try this assembler one more time. Sorry. It's been a week or so since I tried this.
Can you try disassembling it?
Yeah, let me get it into memory first. So line 2, scan DS. Maybe I have to do it with an EQU. Okay. I'm struggling with this assembler is what's going on. So instead of saying scan DS, I'm going to do 1F, 1F. And then jump halt is 0840. And now I'll assemble. Line 18.
Dashes.
It's these dashes. Okay, there we go. Now it's assembled.
Yeah.
Now I can hit upload. Now if I go to 0840, address 0840, there's my A9.
Nice.
And then the next, if I hit plus, what's it going to say right here?
00, right?
BE, because of this.
Right. Because load A, because that's now split between two different headers in memory. One for the instruction and one for the PE.
Yep. And then the next thing is going to be store A, which whatever the store A instruction code is. 8, probably this one, 8D. 85. Well, anyway, it's got my program loaded in any event. We can actually see that if I go over to this assembler, this is the assembly output of our program. And so the general format is it shows the memory address and then the whatever bytes make up this line. So we got So the 85 FB is for that. And then we should see an A9 EE and so on. Make sense?
So
Yeah.
it does. And question, Richard. So when you entered in your memory, you did it as 0x840 instead of 0840 in the assembler tool?
I did this. Oh, in the assembler?
Yeah, when you said upload, there's that pop-up screen and you said like
Oh,
0x.
yeah. That's because this tool is, when you're doing C programming, hex is prefixed by 0x. When you're doing assembly, it's typically $signs. It's
I
just
see.
it's the nature of this particular tool is looking for 0x, like it says up there.
Got it. So basically, if I see a 0x or a $sign associated with a number, it's probably a memory address.
Oh, it's a hex number. It's a hex constant instead of a decimal constant.
Okay.
All right, so there our program is there. And now if I want to execute it, I should be able to get 0840 on the display and hit go.
Yeep. Oh, you should have done both. Oh, except for you needed U, I guess.
Yeah.
Yeah, well, actually, it is possible to do that, and I can show you how. Because I can actually reference these segments independently. But one thing that I want to call attention to on here is I am doing this thing with a jump statement. I'm going
Yeah.
and re-executing it over and over again. And the reason for that is in the hardware of this display, it just scans it once. Notice you may see a flicker here occasionally. I don't know if you can see it through on your screen, but these have to, because of the way the hardware works, these have to be continuously strobed in order to show up.
Oh,
And so if I don't have this jump statement here that does it over and over again, it actually won't display. It'll like flicker it for a millisecond and then it'll be gone. And you may have noticed certain devices are like that, where if you move them around really fast, you can see them that they're actually not continuously on, that they're strobing. And
Right.
that's what's going on with this from a hardware perspective.
Wow.
Okay, so is this making sense to you so far? So I'm going to do one more thing that I can show you.
Well, let's just walk through the program really quick, just in the lines. We're loading BE, we're storing it somewhere. We're loading EE, we're loading that somewhere. We're loading EF, we're storing that somewhere. And then we're running the program that looks at those places that we stored it and displays them on the screen. And then we're jumping back and doing it again over and over again, because if we don't, the screen's going to clear.
Right.
Okay.
That's exactly right. And then it's just the machine's locked up in a loop here, and I have to hit this hardware reset button to get it back. All right, so let's, you were saying we would need a U in order to show Bo's name. All right. So I want to show you some code here real quick. This right here is a program which this prints a dash running across the display. Okay. And the way that they're doing it, actually, you can look at this program and get an idea of what it's doing. I guess the real point of what I'm trying to get at is on this machine, you can actually individually display anything that's physically possible to display on there. You can do it. In particular, the hardware is wired up like this. Okay, and so each one of these little segments is independently addressable, and there's 1, 2, 3, 4, 5, 6, 7 of them, which means that there's 128 possible things that could be displayed here. Does that make sense?
Yeah.
Mm-hmm.
So anyway, this program here that I'm showing you actually makes a dash run across the screen somehow, and so you can sort of get an idea of what it's doing. These things about set directional register. So whenever you program one of these things, there's the chip is physically wired up to different input-output devices. And so they have put some sort of an input-output device at this memory address. And so when they load A to 7F and store it here, they're setting some sort of hardware directional register on here. And then they're doing these other things. So a lot of this, what's going on in this assembly program, is specific to how that hardware is wired up. And so when you get a job as an assembly programmer, your hardware engineer is going to come to you and say things like, okay, so if you want to mess with the display, I have wired in a thing at this address that does this, and a thing at that address that does that. And you just write your program to go work with it. And go ahead, Bo.
I just think that's like really cool. Like it's also how you get those like really like tiny like memory footprints or like games back in the day. You know what I mean?
Yes.
Like they're just
Yes.
directly interfacing with the hardware, which is really that's really cool.
It is pretty cool. Yeah. All right, so we're going to write one more program before we're done. Something that does something a little more interesting, like adding two lists together. All right. So I'm going to show you a slightly more complicated program. Pulling it up now. Yeah, I'll just bring this in over here. Okay. So let's say that we have a couple of lists in memory. So like over at, I'm going to make a subroutine basically. So I'm going to make a variable called list length, which is the number of entities that are in my list. So let's say we have 5 numbers that we want to add together. So actually, I'll go ahead and just do that. So I'm going to say that we have a list. I'm going to go to memory at 0080. And I'm going to say that there's 5 entries in my list. So I'm going to put a 5 here. All right. And then I'm going to make a variable that says where is the start of my list and where is the end of my list. And I'm going to make a variable that, here, actually I should just assemble this and talk through it. So I'm going to put this in and assemble it. Okay, it's wrong kind of assembler. Let's put it in this assembler instead. All right, assemble. Now what? Add list. It's not defined. Hold on, getting my program figured out. Add list. JSR add list. Oh, it's down here. I see. Hold on. I didn't get my whole program in there. There. Assemble. Okay, good. All right, so there's my program. Let's look through at what this program does and how it works. Okay. So we start with some definitions with these equals. So I'm making my own variable called list length, and I'm saying that that's stored at memory location 80, and that's the number of entries in the list. All right, now I've got a pointer, a 2-byte pointer that points to where that list is in memory. Okay, and that pointer is at 81 and 82. So the low byte's at 81, the high byte's at 82. All right, that's the target list. And then I have a source list, which is at positions 83 and 84. All right, and the idea is we've got an array, 2 arrays in memory. They're both of length whatever is stored in list len, And we're going to add those two arrays together. So let's look at the code that does that.
Wait, sorry, me being dumb. So wait, why do you need three different things to reference the list? There's the one's the pointer, then the low and the high.
Yeah. Why? Because our CPU only has 8-bit registers. And so I am trying to store a value that says, here's where my list is in memory. It's at a particular 16-bit location. I have to put the two halves of that address into memory as two separate sets of instructions, because I can only hold 8 bits of memory at a time.
So then shouldn't you only need two to specify the list?
I only have two. Well, let me show you what I mean by that. I have this one location. T-list is a 2-byte pointer sitting at position 81. The high byte is at 81 and the low byte is at high bytes like that.
So that's why 81 is referenced twice. It's like, hey, this whole thing is called T-list, but there's actually two parts of it, the low byte and the high byte.
Yes. And certain assemblers will do that sort of thing for you. But anyway, here's my full program. Load A with 5, store that in list length. All right. And then I'm going to load, I want to set T-list to 0200. All right. So to do that is 4 instructions. First, I load a 2 into A, store that at T-list high. Then I load a 0 and store that at T-list low.
Okay.
Then I'm going to load A with, I'm trying to get source list at 208, and I'm putting in the 2 and then the 8. All right. And then at this point, I can JSR add list. Okay. So before we go look at add list, let's go ahead and set up our data for this program. I'm going to put in, actually we'll set it up in a minute. But the point is that we have set up two lists, one at 200 and one at 208 that have 5 entries each. And we're going to add them together. Make sense?
Mm-hmm.
Okay, yeah. Now let's look at the add list subroutine. And I have documented, this is how you did it back in the day. You would document what are the inputs and outputs to this routine. And before you call this routine, you should have the list length variable set to the length of the lists, T-list set to the target list. Entries here will be updated by adding the values from source list into them. And then source list is our source list. Each entry here will be added into T-list. All right?
So just to clarify, like arguments in this case, they're just consecutive bits of memory. That's like how you specify arguments.
Yeah, it's like a convention. Okay. We're just trusting everybody to be gentlemanly and play nice.
Right. Yeah.
When we call this routine, we expect for this list length piece of memory to be set to the length of the list. And up above, I defined list length to be equal to 80 hex.
Right.
So it's going to go look at 80 hex to figure out what our list length is.
Got it.
And then I also expect these other 2 memory locations or 4 memory locations to be set to the target and source list pointers.
Oh, okay. Yeah.
All right. And so how it actually works, load Y with 0. What does this line do?
It loads Y with 0.
That's right. CLC, what does this do? Let's go look. CLC, it clears the carry to prepare for addition. So let me just explain what this means real quick. All right. Where's my instructions? Okay, actually, I'm going to tell you instead of looking up the manual. CLC clears the carry bit. And you may recall that I mentioned that this thing only has a few registers. It's got A, it's got X, Y. S is the stack pointer. It also has a thing called the status register. And one of the pieces, the status register typically works with individual bits that are in the register. One of those bits is called C. It's the carry register. If I add 2 numbers together using the add instruction, if the total is greater than 255, it sets the carry bit.
Well, and what I don't see on this diagram where the carry bit is, sorry.
It's this, right? You see this, the processor flags, the status register, and then there's this little C right there at the end.
Is it right on the processor flag, like next to Z?
Yes.
Yeah.
Oh, okay. And that makes
So-
sense. It's called the carry. It's
Yeah.
literally like this is what carries over from addition.
Yep. And so if you add two numbers together, the result will always be a number between 0 and 255, between 0 and FF inclusive.
Right.
But if the sum, this tells you if there was a carry. And when you do the add instruction, it also adds in the carry bit from the previous one. So if you're not ready for that, that could give you erroneous results when you call the add instruction. In fact, the add instruction on this particular processor, there's only one add instruction, and it's called add with carry, ADC. All right. And so this CLC that I had in my program here, where did my program go? Right here. That clears the carry, because down here I'm about to do add with carry, and I want to make sure that the carry bit starts off as 0.
Right.
Won't it just be overwritten?
Won't it just be overwritten? It will be overwritten, but the carry gets added in automatically when I do my add. In other words, when I do an add, the new carry bit is going to be set as a result of this add, right?
Mm-hmm.
But in addition to that, the carry bit is an input into the add as well from the previous add operation.
Oh, I see. Okay.
And so I have a clear carry here just to make sure that I don't get funny results on my add. And technically, I should probably be doing something with my carry down in here, because it's sort of an undocumented bug or feature that as I add my values into my list, the carry is going to do something. So anyway, we start with 0, clear the carry. Now this is going to be done in a loop. Load A. This instruction is kind of tricky. We look at memory at the TLST area, and then we grab the address out of that. So TLST, we know, actually I'm going to show you down here. We know that TLST is at hex 81. So it's looking at memory location 81 and getting that and treating it like a pointer. And pointing at whatever memory this 81 pointer is pointing to. Does this make sense?
Mm-hmm.
Then we add Y on top of that. So this is like C-style pointer arithmetic. 81 is pointing to a particular place in memory. And then we grab the pointer that's there, add Y onto that, and that's what we're going to load A with.
Okay. So it's load into A the yth element of the T list.
Yes, that's exactly what it's doing.
That makes sense.
And then we're going to add with carry.
Wait, sorry. One question, Richard. Why is it in parentheses? Is that just convention? Because we're already specifying with the $ that it's memory.
It's because, no, the $ doesn't mean memory. The $ means that the following numeric constant is hex.
Hex, right. I see. Okay.
The parentheses tells you don't just go to memory location 81, but grab the address that's in memory location 81 and use that.
Oh, I see. Because 81 isn't where the list is located. It's where the pointer to the list is located.
Exactly. And that's what the parentheses mean. Then the comma Y means after you've done all that, add Y onto it.
Wow.
And so we start Y with 0. This picks up, this is like, if in C terms, this would be like $, this would be dereferencing a pointer.
Mm-hmm.
Then adding a value to it. Then we're going to add with carry, do the same dereferencing pointer trick on that other pointer that's at 83. And then read that value out of memory and add it into the A accumulator. That's what ADC does. So now A holds the combination of the first entry of both of those lists.
Or the yth entry of both of the lists.
For the yth entry of both of those lists. And then we store it back at that same location from above.
Oh, okay.
Then this instruction, INY, increments the Y register.
This is making perfect sense. But what about if
Yeah.
the addition is overflows.
Then
Like if there is a carry bit, like don't you not have enough space to carry to
it'll
move in?
it'll be sitting in the carry register, and the next time this ADC comes in, it'll carry it in. So that carry bit will sort of propagate left to right, it looks like with the way this code is written, which
Got it. So,
may or may not be a bug depending on what we're trying to do. So for
I
now,
like
I would recommend not trying this code with values greater than 80 hex.
Yeah, this is a
modular arithmetic.
list edition. Yeah.
Adder.
Yeah.
Okay, so I and y, that increments y. Then CPY 80. What this does, I can tell you that CPY stands for compare y. All right? And compare y to what's in the memory address at 80. And what did I say 80 was?
Oh,
List length.
this is like how you break out of the loop.
Yes.
Ah, yeah.
See if y is greater than our list length. All right, B and E, that stands for branch not equal. So if this comparison operation, it's actually a subtraction in memory. And all it does is sets that condition register that I mentioned over earlier. So there's a bunch of bits sitting in the condition register, this thing, the status register. So it subtracts them. One of those bits is Z for 0, and then there's ones for positive and negative and so on. But B and E basically compare Y to the list length. If it's not equal to the list length, then I want you to jump to memory location 41B, which you can see is right
41B
here.
is right on the left there. Yeah.
So
Okay.
BNE, is that literally checking the value of the negative bit?
That's exactly what it's doing.
And executing it?
I think it's checking the value of the 0 bit technically, because if the two things are equal, then the value will be 0. But there's other branch instructions like BMI for branch on minus, BPL for branch on plus.
Got it.
And so on. And so this loop will repeat until those lists have been added together.
All right. So I want to talk about this. Makes perfect sense. We're grabbing the yth element of the first list, the yth element of the second list, adding them together, and what did I and y do again?
Increment the Y register.
Increment the Y register, and we're going to keep doing that over and over again until we finally find that we're bigger than the value of our list on the CPY command.
The value of our list length.
Bigger than our list length. And if we do, we'll get out of the program. Otherwise, we're going to have this go-to statement that goes basically to the top of our program again.
Yeah. And technically this RTS stands for return to subroutine. It's value 60. And when you do a JSR, which we did up here, what that does is it pushes the current program counter address, which would be like this address here, or maybe this one. I can't remember which one it pushes, but it pushes it onto the stack. And then RTS pulls off of the stack. It loads the value that's currently on the stack into the program counter. So it's like a go-to to a specific spot that we saved earlier.
So why are we going to 60?
60, we're not going to 60. 60 is the opcode for RTS.
Oh, so return to whatever called me.
Yes.
Okay. I have a question. Next to LDA 81Y on memory address 41B, it seems that we're just saying B181. Where's Y?
Let me show you. Great question. Great question. So we packed all of this down into 2 bytes. What is this sorcery? Let's look. So remember this, load A81. All right, let's look at the instruction set. I'm going to go to the top.
I think I know the answer to this.
Go ahead, Bo. What do you think is the answer?
Well, I think it's a different opcode than the normal LDA. Like there's actually a bunch of LDAs with different
That's
opcodes.
exactly right. And here they are. So we are doing this style of LDA right here, right? Which is the B1 opcode. And you can see that it's 2 bytes.
Right,
and so
Y is always, sorry, this is me starting to get this. Y is always there. Like we can, like
Yeah.
you can actually have opcodes that reference Y because Y is built into the hardware of the machine.
Exactly. And
Okay.
so if you want to use this style of LDA, then you use this opcode. But if you want to use the plain LDA that we all know and love, that's literal, you use A9. If you want to do the one that looks up the address, you use this one. And actually, they have two different opcodes on this processor. Notice that there's this one, and there's also this one. They look the same, right?
Yeah, other than the number of bytes.
Yeah, so this is a 2-byte one and that's a 3-byte one. So if, like normally in your programs, you're going to want to use this AD one that's 3 bytes. However, if the address that you're looking at is down in the first 255 bytes, also known as the 0 page, you get to use this super cool one that's only 2 bytes long. All right. And now notice the cycles here. All right. This one takes 3 cycles to execute that instruction.
Oh my god. The
But this
cycles
one,
is so cool.
this one down here takes like more cycles, 4
Cool.
cycles. And the reason it takes more cycles is this one takes 2 cycles because the RAM chip, you can only have one address sitting on the RAM bus at a time, right? And so definitely this is going to take 2 cycles because we need 1 cycle to read the opcode. Then we need another cycle to load the next piece of memory. Whereas this one, it's got to go through 2 different bytes for the address. So it's definitely going to take more cycles.
Right.
It's kind of frustrating because like all the programs we've written so far have a lot of like load A store A, load A store A.
Uh-huh.
You think there'd just be like, because we're not even dealing with the machine code anymore, we're dealing with assembly. You think there'd just be like a load and store kind of instruction rather
Oh,
than
well,
having to do
sure.
this
This is a
repeatedly.
very primitive processor, all right? Intel
Interesting, okay.
processors have sheer madness on what they can do with their instruction sets. In fact, you can even pack a loop into a single instruction on Intel assembly.
One other question. The cycles is an actual cost of every single command.
Yes, because
So you can actually score like an assembly programming language in terms of like total number of cycles.
Absolutely, and people do it all the time. In fact, there are plenty of people who may or may not eventually watch this one day, who would look at my program that we just did here, and they would be yelling at their screen, "Oh my God, I can't believe he did this in such a noobish, dumb way." For example, one way to optimize this program is, notice I'm using increment Y. That is a clear sign of a 6502 assembly noob. No self-respecting 6502 assembly programmer would do this. What they would actually do is start at the end of the array, loading the value 5 or whatever the list length is. And then down here, instead of using INY, they would use decrement Y, DEY. And then as a result of that, I don't need this compare anymore because decrement Y will automatically set the 0 flag on the register if it has gone beyond 0, or maybe it's the minus flag. And then they would change this branch not equal to be like a branch on plus. So as long as our value is 0 or greater, couldn't even remember exactly which things I wanted to do, so I just did it this way. But basically, I believe it would be possible to completely eliminate these 2 instructions.
That is insane.
I was gonna say something, but I was embarrassed for you.
Yeah.
Okay, so now that we've been through all that, let's go back to the beginning at how we started, and let's ask some of these questions again. All right, so what's machine language and what's assembly language, and what's the difference? You
so
may not know.
Is what's on the left.
Yeah, that's exactly right. Going into here, this is machine language right here, hex values, and really, if you're a real man, you don't need hex. You use binary. All right, and that's what's going on with this machine right here.
Oh my gosh.
But anyway, that's machine language.
No, he's already taking notes on how to be an assembly hipster.
Yeah.
So this is. Go ahead.
I was just gonna say I built this on Minecraft. Don't worry.
Yeah.
Just kidding.
So actually, you can see though how you would start to make a CPU out of circuits, right? It's like
Totally.
every
Yeah.
cycle, I need to have a program counter. I need to go fetch something out of memory, and then depending on what that opcode is, I need to fetch some other additional bytes or not. And
Yeah.
then I need to have like an arithmetic unit that is responsible for manipulating my A register. You get the idea. So anyway, yeah, this is assembly. This is machine language. This is assembly language.
Yep.
Makes sense.
Okay, and now
Next
back
question.
back to our next questions. How would you write an assembler?
Using machine language?
Well, it's
Or
more, let's say you wanted to use Python. It doesn't even matter what language you write it in. But what an assembler does is it starts with text like this up here, and it produces binary output like that over there. So how would you write that?
It's not even that hard because it's not like a compiler
Exactly.
or an interpreter where it's really smart. It's basically just a lookup.
It's not even that hard. We've been doing it in our heads this whole session, going, okay, I want, for example, load Y, and I need it to be the immediate mode because there's a pound sign here. And so I go over to the instruction set and I find load Y. There it is. What value do I want for my load I operation in that context? Can you tell me, looking at this screen?
Was it? I forgot what it originally was. Did we have the hashtag or the pound sign? We did.
Yeah,
right?
let's look. Yeah, we had load Y pound sign 0.
Okay, then yeah, it would have been just the first one, right? The A0.
Yep, A0.
Yeah.
And then what's the next byte that comes after that?
The value in.
Which was 0, right?
Yeah, I forgot what it was.
So we expect to see A0 and then 0.
Right.
And so right there on add list, where was it? Add list. Yeah, A0, 0, right there. So that's how you write an assembler. We just did some assembly. We did the work of an assembler right there. And then similarly, this guy, load A, $81Y, is just B181 for that whole thing.
We should see the A000 in that hex dump that you have up above too, right?
Yeah, which A00? This one?
Yeah.
Oh, this one, right there. It's at position 418. So.
Oh yeah, there it is. Okay.
There it is.
Yeah.
Okay, so that's actually one of the other questions that I had in my list. What does this mean? Spoiler, it's a program. What does it do, and how would you figure it out? So you guys actually know how to do that now, right?
Yeah.
In theory,
and with this, like, we know that A9 is a command, and BE is what gets fed into the command. And then, so we then already know that 85 is another command.
As a matter of fact, you can probably eyeball this
no.
and guess what this is.
It's not a command. 85 is where it goes.
Nope.
Or no, sorry.
85 is.
A9 is loads BE into
Yeah.
A9.
And then 85 is a store A.
Got it.
That's a store A.
That's actually what would maybe make it difficult to like read this is like, is there an easy way visually looking at this to delineate between commands and data?
There is. It's called a disassembler.
Okay.
You run a disassembler on this and it goes and figures it out for you. But if you do it by hand, what you do is you go, okay, I'm going to assume the first thing's an opcode. What is that? You go look it up. You find out that it's load A. And then this, you go look that up and you find out that it's store A. And we're going to store something at FB. And then A9, that's another load A. Immediate with EE. 85 is another store A. And so this is actually the program that we were looking at earlier where we put beef onto the display. So we got our BE here, our EE here, there's our EF. And then there's our JSR 1F, 1F.
So stupid question. Like on your machine, on your like little green like toy machine that you pulled up, every other instruction is always the command, and it goes like command.
Generally,
input, command,
but
input.
certain things are only a single byte.
Right.
It depends on what the commands are. This particular one happens to be all 2-byte instructions or 3 bytes. Some of them are 3, like this one's 3. There's other instructions though, like INY, for example, that are only a single byte with a single opcode.
But wouldn't but like we would get those then just like 2 zeros in as like the argument to it, right?
No, there is no argument to it.
Oh, okay.
In
I
fact,
see.
let's look at our assembler here. Down in here, INY. Notice that we got these bytes here at position 4F. INY is sitting at 421 memory location, and then the next instruction picks up right away at 422. There's no zero padding or anything.
So if we saw this, we would see like in less parsimonious memory, like if these were stored into on a larger machine,
Mm-hmm.
then it would be like B1, 81, 71, etc. And there'd just be C8, C4. And the only way I'd know that C4 isn't the input to C8 is by looking up C8 and realizing that it doesn't take inputs.
That is exactly right. In fact, if you jump your program into the wrong spot in memory, crazy stuff happens. For example, it would be entirely possible for me to tell it to start execution on this byte right here, which is like part of this other instruction. And things get out of sync and everything gets misinterpreted and the computer crashes. Which is something that happens all the time. But you just have to sort of know where safe spots of memory are to execute and where they aren't. But this is kind of what the memory dump looks like right there. And you get to, when you're working with the computer long enough, you get to where you just recognize A9 and what it is and 8.5 and what it is.
Mm-hmm.
Okay, so back to our list of questions then. So yeah, you now have an idea of how to interpret what something like this means. If you wanted to write a CPU emulator, can you think of how you would start to do that?
Well, we basically just need to execute the different types of commands that we've learned.
Yeah.
Like we need to be able to do load A and
Yeah.
add 2 things with carry.
Yep.
Yeah.
It's just a huge switch statement of all the different things that you might do. And then this thing that looked like alien moonspeak to you earlier, what does this mean?
Right, this might still take me a second, to be honest.
There's an instruction called DEC.
Yeah, so
Okay.
but the result, it takes a pointer, right? So it's decrementing whatever it's stored in that pointer.
Yeah, there's
Correct.
different flavors of it. So you can say, for example, let's say we wanted to reduce the size of our list. I could say DEC and this list length address, and it would go decrement it for me in memory.
Yeah.
And it has several different options. You can either go 0 page, you can use an X offset.
What's 0 page?
That's the first 256 bytes of memory.
Oh, so it's literally starting on 00.
Yep. And notice that you only have, it only takes 2 bytes if you do it that way. Or if you use this style, it takes 3 bytes.
Got it. And I'm surprised there's not a deck where instead of passing in opper, you can't pass in like parenthesis opper.
Yeah, sucks, right?
Oh, okay.
Now,
Interesting.
I can tell you that the 6502 is a very limited processor. It's very crap-tastic, right? Like you would expect all of the various things that we discussed on those other addressing modes to be available here, but they don't do it because it saves transistors. So at the beginning, I mentioned I had one of these TRS-80 color computer, all right? And then there was the Commodore 64. This guy has a 6809 processor in it. This has a 6502. The 6809 processor, when it came out, was like $300, which in today's dollars would be like $2,000.
Yeah.
Meanwhile, the 6502 was $30, So it was like a tenth the price or something. And so that's why it got used in all these consumer devices. But the reason it was so much cheaper is they took all these ridiculous shortcuts in the 6502. In particular, only 8-bit addresses. It's so hard to work with your program that way. Like you'll notice that in our program here, I'm not just passing pointers as subroutine inputs for this add list. Instead, I had to reserve some bytes down there and store them in memory. And these bytes have to be on zero page because this addressing mode where I'm taking a pointer and then adding Y onto it, that only works in zero page memory. There is no variant of this load A that works outside of zero page on the 6502. There's 100 limitations like that in the 6502 that make it totally craptastic, but that's why it was so cheap and that's why it was so ubiquitous. On a 6809, you feel like a god. You've got 16-bit, you've got the X and the Y register are both 16-bit. The A register, there's an A register that's 8-bit and a B register that's 8 bits. You can work with them independently. There is a Y plus mode and an X plus mode where you say, hey, after you fetch this, auto increment it just like you do in C. And a pre-decrement and post-decrement, all of that built into the processor. You can combine the A and B register together into a single register called D that's actually 16-bit. Point is, it's such a pleasure to program a 6809, and I used to be insufferable with my friends at Atari saying, oh, 6809 is so much better. But point is, you've got these limitations that you got to deal with. And if you were to go look at how to program Intel or something like that, it's very much the same way. There's a bunch of opcodes. They do different things. They have different quirks, but the same thing always exists in any assembly language. You're going in and out of registers. You're combining registers with memory in different ways. You're comparing, you're jumping.
So,
The fundamentals are the same.
so I have a question. Like when we often when you go install things and it's like, what version of Windows are you running? Like 32-bit or 64-bit?
Mhm.
It's referring to like this, right?
Yeah.
Like the registry size.
The processor itself can handle only a certain number of bits at a time. And back in the day with the IBM PC, the first one, those handled were they 16? No, they were 32 bits. But it has to do with how many bits it can handle within memory at a time. And then at some
Right.
point, they expanded out to 64-bit AMD processors that could, their load operations and store operations could go up to 64 at a time, 64
Right.
bits. And then
We're
their
talking about
addresses
8
as well.
bits. And we were talking about 8 bits here, and now we're talking about 64 bits. It seems
Yeah.
like way too many bits now for some reason.
Why would you need so many?
Yeah, that's enough bits for anybody.
Richard, so I'm trying to picture. Okay, so like when first of all, tell me if I'm totally wrong here. When I picture someone writing an assembly program, or machine language program, or whatever we want to call this, I picture someone like writing like one of those original Atari games,
Mm-hmm.
because that was written like directly in this type of thing, right?
Yeah, for sure.
Okay. And I'm trying to think about like what the process for that would be, because like the process of writing a large code like a game on like something like this, because you define your functions basically, like where you jump to, just as like I'm just going to put it at this point in memory and go down.
Mm-hmm.
Like how do you possibly make it so you're not like programmers aren't constantly accidentally overwriting each other's methods
Okay.
because they didn't know that something was in that exact spot?
Yeah. All right. Let's talk about that. The process is actually very similar to writing any program. As we've discussed before, the first step is, so there's actually two different questions there. How do you proceed? And then the second question is, how do you stop? How do you avoid writing on top of your memory and stuff? The first step is figure out what you want to do with memory. Or, as we would say in modern programming, figure out your data structures that you're going to want to work with. Once you've established a good set of data structures to express your problem, the rest of the program is much easier to write, or almost writes itself. Okay. So like, for example, to think about it very small, I wanted to add two lists together in my little program, right? I wanted to add two lists together. Where was that? This here. And let me bring it up over here. This. Okay, I want to add two lists together. The very first thing I did was figure out my data structures. How am I going to store my data? Well, I know I want a variable. This is actually kind of the sequence in which I wrote my program. I know I'm going to want something that reflects the list length. So, and I'm going to pick a spot to stick it. Let's put it at 80. All right. And then I know I'm going to want 2 pointers. So I'm going to make 2 different pointers for the source and target list. And I made those. Okay. And then in a real program, it would be much more complicated. Suppose it was a game and we want to have little enemies running around that can be killed. And so we're going to make a data structure. And we know that we want how many hit points do they have and what kind of critter style is it, and, you know, what is their position in the map and so on. And so we start to figure out how we want them to look. For each one of those attributes, we decide, do we want to make like a structure that holds 1 per critter, where the first 2 bytes is the critter type and the next 2 bytes is their location and the next byte is their memory? Do I want to do it that way, or do I want to say I've got an array of 100 critters and I want to store those things separately? Like I can have this array here of up to 100 critters is all of the critter types, and then this next array of 100 bytes is all of the critter hit points. And so basically you start to figure out what you want to do with your memory. What data structures do I want to describe my stuff? Then once you have figured out what your data structures are, you start writing routines and build your thing up a little bit at a time. Maybe the first thing you want to do is get your graphics to clear the screen, and now I've got my array of critters. I want to make a subroutine that shows all the critters on the screen. So I start writing it. All right. Well, we've got a byte here that says how many critters there are, and we're going to loop through all of those, and then we're going to display the first critter, and you just keep evolving it. So that's my answer to the first part of your question. How do you proceed? Start with data structures. Now, the second question, how do you accidentally not step on each other's toes? The answer to that is you don't track where everything is manually. You let the assembler do that. The way I wrote this code here is not what you would actually do. What you would actually do is instructions like this. There's these instructions that look like this. They're actually assembler directives. And it's things like, I might make a thing called critters. All right. And I just say like reserve memory byte 2. And this is then I'm going to give it a name, mob count. All right, I might have an instruction like that. What this does, this reserves 2 bytes at this location and calls it mob count. All right, this is what a typical program might look like. We are going to memory location 400. And I have 2 bytes here called mob count. And then I'm going to have, maybe I have a level num, and that's 1 byte. All right, and I just start making up variables. And now this one here is the assembler remembers that this is at 402, right? And this is at 400 through 401. And so basically, you don't actually manually put things into particular memory addresses. You just sort of say, I'm going to start doing stuff at this memory location and let the assembler figure it all out for you.
Then this code, like, where is it stored?
The source code is stored in like a file, like .s, a .s file or something, and then you run that through an assembler, and that produces an object file that looks something like this. And then you run that through a linker, which takes these and makes a binary file out of it.
Okay, so wait, the people who, and this is me knowing nothing about the history of computation. So, you know, I guess whoever's an hour and a half into this video with us will judge me. But like, so the people who were like writing the Mario game, like had access to things like file systems and stuff.
Yes.
Okay.
However, that way back that far, they were actually using like mainframes and timeshare systems and computers like a VAX, VMS, or something like that. But you would actually like literally dial up on a terminal to a shared computer and type your source code in and then run it through an assembler, or maybe you would do it with punched cards or something like that.
It's just weird because I I figured that all the file system type stuff would have come after like people were using higher level programming languages on the reg. Like that people would be like doing things in C by that point. I didn't realize that people were writing like assembly or level programs while they had access to things like file systems and stuff.
Oh yeah, people absolutely used file systems while they were um, while assembly was being used all the time.
Interesting.
But either way, even if you didn't have file systems, like going back even further, you would have like punched cards or tape, and you would put your source code onto a tape, and then you'd write in a there'd be an assembler program, and somebody would load your tape onto the machine. They'd first load the assembler, and then they'd launch the assembler, which would start loading your program off of tape A and then producing object code like this coming out onto tape B.
And then you'd put that into your personal computer.
You put that into your computer and hit the boot button, and it would load the tape and start executing.
I never want to hear.
Wow, that really does make it feel like a computer. Like it just computes these numbers, and you have to
That's
get them
right.
somehow.
That's right. And have everything all set up just perfectly. And that's why computer operators were well paid, because that's like takes a lot of skill. But anyway, just to wrap this up, let's look and see if you have a feel for the rest of these questions then.
Sure.
Yeah. All right. How do you code in machine language or assembly language? You've got that idea. How would you hack or modify a game? Back in the day, on this computer right here, there was a little cartridge spot that you could plug stuff in, right? So I'd buy a game as a cartridge and I'd plug it in. And the way that cartridge worked is when you reset the computer, what it does is it goes to memory location FFFE, fetches those 2 bytes out of memory, and that is the vector where it starts executing. All right. The ROM that you plugged in here was actually mapped into memory up at the high area of memory. So when I plugged my cartridge in and hit reset, it would look at the ROM, pick up a memory address, and start executing. All right. I used to hack my computer and pirate games by taking a little piece of tape and putting it over 2 of the pins on the cartridge that would prevent it from loading that high piece of that vector of memory. And then I could go read the contents of the cartridge and write them out to a cassette tape or something like that. But in general, your program is going to be in ROM or in memory. You write that memory out somewhere, and now you've got stuff that looks like this, and you can see what it does, and you can actually make modifications to the memory here as long as you don't change the byte positions. For example, you could take these first 2 instructions and turn them into a JSR of something else that goes and does some other things, then continues and does whatever these instructions were, and then does an RTS. And now you've just made a modification to your program.
Did you modify any of your games?
Oh, all the time.
Like
Yeah.
what?
Oh, for example, I pirated a game, and I changed some of the things that it said to the screen and made it, say bad words to my friend and stuff like that. Just dumb stuff.
Okay.
Okay. All right. Yeah, I think you actually know how to do all of the things. Back to where I started.
Okay.
So when I was a boy, like I mentioned, I saw that as just completely inscrutable dark arts right there. But now, hopefully you have the tools to where if you felt committed, you could figure out what this program actually does without executing it.
Shall we try?
Well, yeah, let's try. 162. This is all decimal though. That's part of the trick. So 162, we've got to convert that into
Wait, what's data? Sorry.
that's just what this does is it's just embedded data, and then the read statement up here reads the first value. So this read Q takes 162. And the next time through this loop, it'll take on the value 1. And it just advances through.
Oh, next D is next data.
Next D goes back up to the loop that starts on line 20.
Oh, I see. Okay.
All right, programmer. So I want to take 162 in decimal and convert it to hex. That's A2. All right. So now we come over to our instruction set and I search for A2 in here. That is a load X immediate, which means the next 1 byte is what we're loading into X.
Right.
So where was my program? Oh, it's in my OneNote right here. All right. So load X with 1. So that's load X1. We're not going to do the whole thing, but let's look at the next one. 169. All right, I'm going to convert that from decimal. And by the way, this is what a disassembler does. We are being a human disassembler right now. That's A9. All right, A9.
You know, they've been telling me to worry about
There
my
it
job
is.
getting automated, and I think
That's
this human disassembler thing might just not last.
That's load A immediate with whatever the next byte is, which for some reason is shown as pound sign, pound sign, pound sign. But let's just say that it's 42 and so on. And you can go through here. The next one is 201. Let's just do one more. 201 decimal hex is C9. What is C9? It looks like a compare X. Come on. There it is. Compare immediate to the next byte. So that's CMP 200. And then 144, I'm just going to gamble that 144 is some kind of a branch instruction.
Because we're
140.
comparing.
Yeah, because we're comparing. That's 90. Branch on carry clear.
Nice.
And then the next byte is 15, means it's going forward 15 instructions. So it would be down here somewhere. Whatever 15 bytes forward is, that's going to be where it's jumping into.
I see. So it makes sense to me then that you're literally just looking up the values here and seeing what they are, and
Mhm.
you're kind of tracking in your head, does this thing take arguments or not, to decide,
Yeah.
if they
And I
belong
don't even
together or
have
not.
to I don't even have to track it in my head because this right here tells me whether it takes arguments.
Right. I guess what I'm kind of curious about is, like, why do they do that? Why don't they just load the program like this? Why are they using this for loop thing that reads that?
Why don't they do what?
So can we go back to the program? So
Mm-hmm.
we have this, like, 4D equals 0 to 73.
Mm-hmm.
Like, it's saying, is it saying basically, like, execute this program starting at 100? Or what
No.
is this for loop doing?
This for loop is saying I have 73 data values here. If I were to count them, this is going to be 73. So we're going to execute line 30 73 times. Is what that's saying.
Is that basically loading this program into a different part of memory?
It's loading this program into a different part of memory. Exactly.
Oh, okay. So this is sort of how, I guess this is a program that, like, defines a function basically, and the function is defined on 100 to 190, and now you can use that function wherever you want.
Exactly. Well, what it's doing is it's loading this stuff into memory at position 828. And now you can use this sys828 could be invoked from anywhere once it's loaded into memory.
Got it. So maybe this is a program that might be generally helpful, and if you run this program now, it's sitting on your computer so that you can use it.
Right. And this is actually like a woefully inefficient way of doing things because the program's really in memory in a couple of different ways. It's sitting here with all these data statements, and then it's also poked into memory at 828. But
Yeah.
But anyway, so now I wish somebody had gone through this with me because I thought that this sort of thing was the realm of computing demigods. and it's really not that bad.
It seems extremely difficult.
Yeah, I was like, it still feels pretty bad.
I mean,
It's
like
really
you've
awful.
explained it in a way where I understand. I feel like I could step through an assembly program and maybe start to figure out what it meant. But the idea of being able to take all these different things into account and storing random parts of the program and random parts of the computer and having to kind of remember where you put things and then having to wait for the assembler to do stuff before you can program anything at all. Like it sounds horrible.
Yeah. Here, I just want to show you a couple of games that are written in assembly. Oh, these are terrible. I want to find one that's actually okay. So here's a chess game. Who knows what it does or how it works, but you can see that, with some study, you could probably figure it out, right?
Yeah.
Um, but I just want to show you one of the geekiest, nerdiest things I've ever seen. I thought I was a nerd, but here is a game that you play on the Chem, all right? And this is called Chem Venture. Chem Venture. There's the source code for it. It's not the source code, that's the object code. But it came with this manual. Okay, this is from 1979. And apparently, the way, if you skim this manual, there's all this stuff about how to load it. But there's one computer operator, and then there are one or more players that are the actual players that are playing the game. And the operator collects moves from the players. Don't peek. The operator provides pencil and paper, and you do all this geeky stuff. And there's a map that came with the game that looks like this, and you sit down and you play it. I mean, how geeky is that? Anyway,
Well,
that
this
is
seems like
all.
your vibe.
What?
Seems like Bo's vibe is what he said.
Oh, yeah, it's like
Map game?
it's like it's like for really intelligent like D&D players. That's what they do for fun. I don't know how else to describe it.
All right. So to show you how transferable this is, I'm just going to show you. This will be my last thing, and then we'll depart.
Okay.
RISC-V assembly. So RISC-V is a different kind of processor. Hold on. And we're just gonna like look at this, and this should mean a lot more to you now that you've learned about this other. So RISC-V is a modern processor. It's an open source one. General registers.
All those registers.
I know. What are you even gonna do with that many registers?
Oh, that's sexy. Look at that. How many registers is that?
I don't know, 32 or something. But basically, it's
Yeah.
so many registers that basically it's up to the compiler to decide what to do with them. You don't even write assembly with it. Like, I mean, you could, but there's 32 registers, it looks like. Instruction set. Let's just take a look. All right, here we go. Here's some RISC-V assembly.
What is B equals? It's some kind of comparison.
Branch on equal. I guarantee you that's what
Branch
it
on
stands
equal.
for.
Oh, that's right. I see.
And so look, add all three of those registers together.
Oh my god.
And
How advanced
then
this is.
branch on equal. This looks like it's comparing, like, does A1 equal A5 and whatever .L2 means? And then add all three of those together and then move. Oh, Jackson, this is what you were talking about earlier. We were talking about load A, store A. This is a combination of load A and store A. So, or sort move from A0 into A5 is what that looks like to me.
Wow. This seems
But-
like the future.
Yeah.
Yeah.
I think things are
Everyone
going to
just
go in
needs
this direction.
Ooh, look at this instruction.
B set Vili.
I'm guessing that's some sort of a mem copy type of a thing.
we can't, like, this is coddling the kids too much, you know what I mean?
Yeah.
Yeah,
Shouldn't be allowed to have all these
they're
fancy
going to be
things.
weak and
They're
Yeah,
gonna be
frail.
weak. Yeah, you guys,
Frail.
you were
Yeah.
brought up strong on 8-bit machines. You didn't start with these modern processors.
well, it's like
Kids these days.
you learned like how to program on this like 8-bit thing, and like I learned how to program like doing Python in the browser for a website that compiled it for me. It's insane the difference.
True, man.
But you can see that you're equipped to at least start to understand where,
Yes.
and you would know, all right, what the hell is this? And you'd go look it up. But you don't feel like overwhelmed right away.
No, this makes sense. It's very linear, actually. It's just execute these instructions, and if you know what each of them means, it's going to be okay. And what they can mean actually can't be that crazy because it's something that's actually getting physically executed by the CPU.
Yeah. And one thing I will tell you about modern processors, they don't actually, like Intel at least, doesn't actually execute what you see there. What it actually does is it just like it's got a front end and a back end internally. It takes those things and it's basically got a virtual machine that's actually executing the stuff, and it's saying, "Oh, I see that I can execute these instructions in parallel because the results aren't actually going to do anything until 5 cycles later." And so it's doing crazy, mind-blowing stuff. But anyway, that's assembly language in a nutshell. If somebody had told me this talk back then, I would have been way, way far ahead of where I am today because
Well, I think we're finally at the 13-year-old Richard level of computation.
Thank God.
It feels good. This is like that like chess app where like you can play Magnus Carlsen when he's like 8 and he like completely destroys you. Thanks, Richard. This is awesome.
Yeah, that was really good.
did it demystify it for you?
Yeah.
A lot. Yeah,
Yeah.
I think. Yeah, I don't know. I really like. I've seen those hex dumps before, and I have never really understood them. And I think that helps a lot, actually.
Addresses on the left, values are on the right, and then they'll have an ASCII translation a lot of times as well.
I think it's
So
so
cool.
funny too that like Bo, like at one point you called the # hashtag and like
Yeah.
someone like learning assembly and calling the like decimal reference or whatever.
Yeah.
Like, hashtag is so funny.
It's like one of them is just a decimal value, the other is trending.
Yeah.
Yeah. That's right. Oh man.
All right.
Yeah, this is really cool.
I'll talk to you guys later. Thanks for doing that with me.
Thanks, Richard.
Fun.
See ya.